Hello, and welcome to this video that accompanies our paper titled Learned Multi-Agent Real-Time Guidance with Applications to Quadrotor Runway Surveillance. Aircraft runways need to be periodically inspected for debris or damage. To do so, air traffic is paused while an operator drives a truck down the runway to perform this inspection. To minimize the downtime of the runway, researchers have turned to remotely piloted aircraft to perform a similar inspection. In this work, we use quadrotors to perform a runway surveillance. Instead of using pilots to fly the aircraft, we develop a system for autonomous flight. And instead of developing that autonomous flight system by hand, we use machine learning to design it for us. This results in a highly flexible, multi-agent cooperative runway exploration algorithm that was very easy to design. The end result is for us to be able to place an arbitrary number of quadrotors on the runway in any initial location, and have them autonomously, quickly, and cooperatively explore the runway. We use deep reinforcement learning to allow the quadrotors to learn how to explore the runway themselves. Reinforcement learning is a branch of machine learning that seeks to learn a behavior in order to maximize the rewards received. In this 2013 paper, deep reinforcement learning was used to master Atari games using nothing other than the screen pixels and the feedback from the score of the game. In attempting to maximize the score received, the agent indirectly mastered the Atari game. We have two runways at our disposal, an indoor one shown on the left, and an outdoor, much larger runway shown on the right. To generate our score, also called a reward function, we divide the runway into a set of 32 tiles. Each time a new tile is explored, we give the quadrotor a reward of +1. When multiple quadrotors are used, we penalize them for getting too close to each other to encourage independent exploration. Through trial and error, along with the learning algorithm, which is described in the paper, the quadrotors learn to cooperatively guide themselves to explore the runway. We should note that to explore a tile, a quadrotor simply has to pass over any part of that tile. Here are some simulated results after training was completed, showing one quadrotor exploring the indoor runway. The tiles become shaded as they are explored. Next, we exported the trained guidance model to a real quadrotor in an indoor facility. The quadrotor first takes off, maneuvers to its initial position, and then listens for commands generated by the machine learning algorithm. You can see a sped up video of the flight here, but the results become more clear when we look at a plot of the trajectory. These 4 plots show snapshots of the trajectory at different times during the flight. You can see that the quadrotor intelligently goes after tiles that have not yet been explored, and after 23 seconds successfully explores all of them. We then repeated the training with 2 quadrotors and performed a similar experiment shown here. You can see from these 4 snapshot plots that both the red and the black quadrotor shared the territory that they were going to explore, and they kept their distance due to the proximity penalty in the reward function. This coordinated flight was learned entirely on their own. The only input from the designer was to specify the reward function. Now that the technique has been demonstrated in an indoor controlled facility, it is now time to apply it to an outdoor, GPS-driven, real-world environment. This is a bird's-eye view of the runway we use for outdoor experiments. And these are the 2 quadrotors used during the outdoor flights. They were developed in-house. Here is a view of the quadrotors taking off to begin their experiment. The quadrotors first maneuver to their initial conditions, and then they're switched into deep guidance mode where they begin listening for trajectory commands from the trained model. We developed 3 different scenarios for the outdoor flights. A single quadrotor exploring the runway on its own, 2 quadrotors exploring the runway together, and 2 quadrotors exploring the runway, but in this case 1 quadrotor fails mid-flight. It was difficult to film the entirety of the outdoor flights due to the runway being so large, but here are a few short clips of the quadrotors flying as guided by the machine learning model, and then I'll show some plots of the trajectories. Here are the trajectories flown of the 2 outdoor quadrotors, working cooperatively. You'll notice that the red quadrotor explored the top portion of the runway, while the black quadrotor explored the bottom portion. This is entirely based off of their initial conditions. They were not programmed to act this way. The flexibility of this approach is even more apparent in this next experiment. Here, notice that the red quadrotor explored the bottom portion of the runway, while the black quadrotor explored the top portion. You'll also notice that in the second frame, there is a red X drawn through the black quadrotor. This indicates a simulated failure. The red quadrotor, upon noticing this failure, completes the exploration of its own side, followed by traveling to the top portion of the runway to explore the remaining tile. Since the flown trajectories are generated in real time using the machine learning model, the quadrotors can be placed in any initial conditions and will still successfully explore the runway using a trajectory tailored to those initial conditions. In addition, a quadrotor failure can occur at any point for either quadrotor, and the exploration will still succeed. This flexibility is one of the major benefits of learning-based approaches. Another benefit is the ease of designing these behaviors. All we had to specify was the reward function. Learning-based approaches do have their drawbacks. The training time can be significant and require a lot of computing power, and though performance can be shown to work in many situations, it cannot be guaranteed to work. All of the details of this work, including the learning algorithm implementation, the guidance and control design, more results and comparisons, and the hardware implementation, can all be found in the paper. All the code used is open sourced on GitHub as well. Thanks for watching.